All right, so what we're going to be looking at now is we're going to actually work to change a linear transformation to a matrix and vice versa. So we've got T, and T is a linear transformation, and A is going to be the matrix associated with T. Okay, so what we want to do, our goal here is to actually take a linear transformation, turn it into a matrix, and then take a matrix and turn it back into a linear transformation. So what we're going to do is we're going to say, okay, well, I want to define my linear transformation T going from V to W. Okay, and so the dimension of V is going to equal N, and the dimension of W is going to equal M. So I'm going to imagine, let's take, for example, we want to take T, and we're going to go from R3 into R2. Okay, R3 into R2. And so consequently, that means my inputs for my matrix that I'm going to create here, if I have a matrix for the linear transformation, is going to be x1, x2, x3. Okay, it's going to be three-dimensional, and my output is going to be y1, y2. So it's going to be an R2. So I'm going to multiply by three-dimensional vectors, R3 vectors, and I'm going to output into R2 vectors. So what I'm going to do now is I'm going to figure out what kind of matrix that I'm going to need for that. Well, one, I'm going to need 3 columns. I'm going to need 3 columns, okay, because I need to be able to take the dot product. I need to be able to do this this multiplication. I have to be able to do that. And then I'm going to need 2 rows, okay, 2 rows, and that's because my output space is 2-dimensional, okay? So what we're going to see here, remember we're going to say the dimension of V is equal to N. Well, in this case, right, that means that N is 3. 3 is the number of columns. So A is, okay, 3 is the number of columns, my input space, and my output space is 2-dimensional, and that goes with the number of rows. There's 2 rows there, so A is 2 by 3. Okay? So basically, this kind of just demonstrates that if the dimension of V equals N, and the dimension of W equals M, then A is M by N. And sometimes it's a little tricky to kind of remember. I mean, like, basically I have to draw, you should have seen how many times I actually had to redo this thing. I have to kind of draw the matrix or draw an example matrix to kind of keep everything straight for me. Basically, what that is telling me is that the dimension of V is N, so that's the number of columns. And the dimension of W is the number of rows. And that's it. Okay? And so this is going to become a guideline for us to be able to actually go in and generate these matrices of linear transformations. So now we have a theorem that's actually also going to be kind of helpful for us. And the theorem is this one, okay? So we've got T. It's a linear transformation going V into W, okay? And we define T of X equals AX, okay? Where A is an M by N matrix. So what that means for us is that, right, okay, my input, that means V is n-dimensional, and M is n-dimensional. Oh, excuse me, W is m-dimensional, okay? Then we're going to define what that's going to give us is that A is going to equal T of E1, T of E2, all the way out to T of EM, T of EN, excuse me, T of EN, okay, T of EN, where E1, E2, so on and so forth, En is the standard basis for V. So basically, if we could figure out standard basis of V. So basically what we want to do is we want to actually be able to figure out what the linear transformation is under the standard basis. All right, we're going to do something actually really, really basic here that's going to kind of help us do this. Going to make things really, really quick. But if we're given the transformation vectors, then it's actually pretty simple to figure out what the matrix of the transformation is. Okay. In addition to that, we can actually just go in and utilize those standard basis vectors in order to generate for us the matrix. And we'll see how that gets done in just a moment. Okay. So we're going to use this, right? And this is, by the way, this is called the matrix of T. So this is called the matrix of T. So let's say, for example, I've got T of x1, x2, x3 equals, and this is going to be negative x1 plus 3x3, negative 2x3, 2x1 plus 5x2 plus minus 9x3, and negative 7x1 plus 5x2. Okay? So I'm going to look here, and so this is, if we notice here, T is going to take vectors in R3. So T goes from R3, and how we know that is we got 3 inputs, x1, x2, x3, into vectors in 1, 2, 3, 4. So it's going to go into R4. So we're going to go from R3 into R4, all right, which means that A is 4 by 3. So A is going to end up being 4 by 3. All right, okay. So 4 rows, 3 columns. And so what I do normally, like what I could do is I just start out with the standard basis vectors for R3. So that means that T of, and I'm going to write them as column vectors, 1, 0, 0 equals, and then I'm just going to plug in for x1. So this is going to end up being the first term here, okay, because my output vectors are in R4 now. The first term is going to end up being negative 1, because it's negative 1 plus 3 times 0. Okay, right? Just notice that I'm just using that. Then it's going to be 0, because x3 is 0. Then we'll get 2x2, okay? And then we're going to get negative 7. Okay? So that ends up becoming the first column of A. So if I'm generating A is going to equal like, it's going to look like this first. Okay? So it's negative 1, 0, 2, negative 7. That's our first column. Now our second column, we got T of 0, 1, 0. And that's going to end up equaling, well, no x2s in the first term, no x2s in the second term, so it's going to be 0, 0. I got 5 x2s, 5. And then 5 x2s in the fourth row. So that means that my second column is 0, 0, 5, 5. Okay? Just notice all I'm doing is I'm plugging in now the 1 for x2, a 0 for x1, and a 0 for x3. And now T of finally 0, 0, 1. So everywhere where I have an x3, I'm going to multiply that by 1. Everywhere else is just going to 0 out. So this means I've got my 4-dimensional vector. It's going to look like this. It's going to end up being 3, negative 2, negative 9, and 0, right? Okay, 3, negative 2, negative 9, 0. So we put that in there, 3, negative 2, negative 9, 0, and there's the matrix of the transformation A. Done. Okay? Couple things to notice here. Notice that here, if we just took the x1 terms, the x1 terms here are going to have negative 1 x1, 0 x1s, 2 x1s, and negative 7x1. There's our coefficients, right? Okay, there's our coefficients. So this essentially is, or not essentially, it is exactly negative 1, 0, 2, negative 7 times x1. So just taking those coefficients, that ends up becoming the first column, by the way, column, right, in the matrix A. Look at the second column. The second column, we've got 0 x2s. If I write that in terms of my x2s, I've got 0 x2s, 0 x2s, 5 x2s, and finally 5 x2s. Okay? And that ends up becoming the second column. And there we go. And so basically what you can do when you get adept at this kind of thing is you can just look at the linear transformation and set up the matrix. Okay, and that's basically what you would do. Let's take a look at another example. So let's consider this example. We got t of x1, x2, x3 equals 4x1 minus x2, 5x1 plus x2 plus 4x3. And so we now want to find a. All right, we could go in and use our standard basis vectors, but remember what we did. What we did basically is we said, okay, let's take the coefficients. Well, actually first, we need to get that t is going to go from R3 into R2. Okay, so t is, or excuse me, a is 2 by 3. So a is going to be 2 by 3. So essentially what we're going to do here is we're going to say, okay, well, look at my x1s, right? My x1 has a 4 as the x1, 4, and then 5. Okay, so the first column in A, now we're going to go by columns here. The first column is going to be 4, 5. Right? 4x1, 5x1, that's 4, 5. There you go. The next column, column 2, is going to be negative 1, and then 1. And then the third column, there's 0, x3's there, so it's going to be 0 and 4. And that is A. And there is your matrix of your linear transformation. Now let's talk about transforming back to the linear transformation. Let's take A, and we'll see that A, right, is going to be 4, negative 1, 0, 5, 1, 4. Okay? And so, instead, when we actually went from linear transformation to matrix, we went and we kind of generated the columns. Now we're going to read along the rows to give us back our linear transformation. So T1, we know that T is going to go from, right, R3, 1, 2, 3, into R2. Okay? And that is because N is the number of columns, and it's going, excuse me, N is the number of columns, that's right. And, yeah, N, the number of columns, okay, is going to be our input space, and M, the number of rows, is our output space, right? Remembering V and W. So, we're going to go R3 back into R2, and you can actually look at this there too. And what you'll see is that means that T of R3 is at X1, X2, X3. It's got 3 components, and then it'll equal, and we just read straight across. This is going to be 4x1 minus x2 plus 0x3. See that? 4x1 minus x2 plus 0x3. And then 5x1 plus x2 plus 4x3. Get rid of your 0x3 because you don't need it. And there's your linear transformation. All right, so let's say, for example, we have t. We're going to go from v to w. And we're going to let a equal 2, 1, 3, negative 1, negative 5, 3, 0, negative 4. Okay, so our input space is going to end up being R2. So V equals R2. Okay, and W is going to equal R3. R4. So we've got T is going to go from R2 into R4. So we're going to have to find what is T of X1, X2. And it's going to end up giving me a 4-dimensional vector, right? So we're going to have 4 answers. 4 answers after each one of our commas. The first one is going to be 2x1 plus x2. The second one is going to be 3x1 minus x2. Okay? The third is going to be negative 5x1 plus 3x2. And then we'll have 0x1 and then negative 4x2. And there is your linear transformation. Notice it has 4 outputs. Okay, its output vector it has 4 components. So essentially, what we want to see is we want to see the relationship between our linear transformation and the matrix of the transformation. Basically, this linear transformation defined this way, going from Rm to Rn, is really easily we can really easily generate a matrix of that transformation. Okay. Let's actually take a look at, like, for example, an example where what we have to do is we have to transform something that's in, say, a polynomial space. Okay, so let's look at that. So let's take a look at this example. We're going to go from R3 into P2R. Okay, so this matrix is going to be 3 by 3. And the reason why it's 3 by 3 is that the dimension of R3 is 3. The dimension of P2R is 3. Okay, so hence 3 by 3. Our input space is three-dimensional. Our output space is three-dimensional. So we're going to imagine that I'm going to end up with my A here is going to equal some 3 by 3 matrix. Now, my first input is going to be the A's. Okay, and what you want to remember on a polynomial, when we take a vector in R2 into a polynomial, or excuse me, in Rn to a polynomial, okay, to polynomial, or polynomial into Rn rather, it should be this way, sorry, that way. That what we're going to do is our top term is, this is the constant, and then we're going to have the x term, then x squared, then x cubed, so on and so forth. So all the way down to xn. Okay? All the way down to xn. And so consequently, I've got to actually start over here. All right? I got to start over there with the constant term. And notice that A is my first term here, is a 1 in that constant term. So this is going to be a 1. And then I go to x, the x term, there's no a's, 0. And then finally, I have 1a. So it's 1, 0, 1. Okay? Next term is going to be the b terms. And I'll notice that I've got negative 2 b's, 2 b's, and no b's. And there we go. Okay? And then my third term, my c term, okay, which will be my third column, I've got 1 in my constants, negative 1 in my x terms, and 0 in my x squared terms. So this is A, the matrix of our transformation. If I want to go backwards, what do I need to do? Well, this is going to then be, okay, I've got to actually go backwards, okay? So what that means is that this is going to be my constant term, this will be my x term, and this will be my x squared term, okay? So I've got, right, here's A, here's B, here's C, x1, x2, x3, and then over here is constant term, x term, and the x squared term. If that's, problematic for you as you're working, right, okay, then you might just want to use the standard basis vectors. But if I look here, I can actually now generate this. This is going to be, my constant term is going to be A minus 2B plus C, okay, A minus 2B plus C, okay, there's my constant, plus 2B minus CX, plus then AX squared, because there's no B or C, plus AX squared. And there is T of A, B, C again. Okay? And so if we're working in, say, something that's not necessarily Rm to Rn, we can still actually, or excuse me, Rn to Rm, we can still actually generate our matrix utilizing some kind of like quick work. If you are in fact, uncertain of how to do that, just go back and use the standard basis. All right? But this sometimes can make this process a whole heck of a lot quicker.